We're very happy today to have Jiangping Hu of Institute of Physics, Chinese Academy of Sciences, to give this Frontier Condensed Matter Physics seminar. Jiangping and I know each other for many, many years, even when he was actually a student at Stanford with Shuchen, and then he later moved to Purdue University, and more recently he's been working at the Institute of Physics, Chinese Academy of Sciences, as a chair professor. So Jiangping is very well known for many of the things that he have discovered, but he particularly liked this topological physics in iron-based superconductors. And he developed his sort of own theory, actually many years ago, first published in PRX. And he's going to try to tell us, the evolution, I guess, his theory over the years on this topic. Yeah, thank you, Jiangping. It's all yours.
Okay, thanks, Penton, for introduction. So thanks also for inviting me to give this seminar. So I will talk about topological physics in iron-based superconductors. This has been started from in my group has been like almost 10 years. So so on this here, you can see a lattice of iron-based superconductor. Here is a picture for the topological physics. We published it in a cover of a journal. Or not moving? Okay. So here's the outline of my talk. I will first make introductions and discuss motivations. Then I will move to the first topic, which is band topology in iron-based superconductor. So this is actually the first part of topological property in iron-based superconductor and has been experimentally tested. So I'm not going to give overall experimental progress in this direction. There are many talks by other people, but I will illustrate this concept called the connate topological superconductors. And then the major part I try to will talk about the topology and the pairing symmetries in iron-based superconductors. So I try to use the topology to distinguish different pairing symmetries in iron-based superconductor. And finally, I will make a summary. So iron-based superconductor was discovered in 2008 and almost 16 years ago. And over time, we have so many different iron-based superconductor material discovered and named by like 1111, 122, 111, these digital numbers like this. And there's many families. And so basically you have two classes. The first one is called iron pnictides. And the second one is iron chalcogenides, and they both are superconductivity up to like 50 K transition, highest ones. And hello? Yeah. So there's also like single layer iron selenium on the STO can be go to like 60K and these type of things. So they all have like basic structure things. This is iron arsenic layer or iron selenium layer. They are responsible for superconductivities. And actually, the iron-based superconductor, as I said, started 2008. At the same time, this topological insulator, which like started 2005, like 6 at that time. So this two field is almost has started at the same, just separate a few years. But in research, actually, there's no overlap. At that time, the two, I think, the most hot field in condensed matter physics. But for many years, they actually does not have any overlap. RMB superconductivity and topological materials are mostly focusing on other things. So for me, it's like I get interested in topological superconductors. So topological superconductor is actually in the nature is very simple. If you have a p wave triplet, paired superconductor, that will be a natural topological superconductors. Also later, there's another proposal which you can use in this topological insular surface state. And if it's a surface state in proximity to the superconductivity, the proximate effect will make this surface state to be a superconductor and just like a p wave superconductivity. So basically, there's two ways to create a topological superconductor. Either you find a p wave super material, like a paired material. Like early days, there's a lot of study on strong loosenate. But now we know that strong loosenate is not a p wave superconductors. So in the nature, actually, to try to find a p wave paired superconductor is very difficult, and it's really difficult and rare. So far, we haven't identified a single one which has definite p wave paired superconductivity. The second one is, I think, is an approach which is complicated and typically also using the low temperature superconductor to do it. But then there's another question which you will always raise, whether we can use a high temperature superconductor to make these topological superconductors. But high temperature superconductors, they always have short coherent length, so it's not good to be used as a proximity effect. So another issue in the iron-based superconductors is that we want to understand the pairing symmetries in iron-based superconductors. So this is I think it's still some experiment fact. So if you look at the iron-based superconductors, and you will find that there's very little experimental evidence to support a Liouville space sign change of all the parameters. So we do not have this like D-wave superconductor like equilibrates, and you have the phase-sensitive measurement to prove that in iron superconductor there's a Liouville space like sign change. Also, another factor is also I think it's clear that is no symmetry practical nodes like a D-wave superconductor. So this without these two things, like the result, I think it's very clear. The iron-based superconductor probably is S-wave with S-wave pairing symmetries. Or another way you can say is S-wave pairing must be dominant in iron-based superconductor. But there's also a lot of question. Well, what kind of S-wave look like in the iron-based superconductor? That's a lot of theoretical proposals on these directions. So how to distinguish these different S-wave pairing symmetries is a big issue in the iron-based superconductors. So here, what I try to say is that in this talk is just try to convince you that iron-based superconductor is actually a topological material, and allow us to create topological superconductor high temperature and really marginal fermions, and also I think these topological properties can help us to distinguish like pairing symmetries in the iron-based superconductor. That's the major message I try to tell you in this talk. So first, let me talk about the band topological in iron-based superconductors. The statement here is quite simple. I will call this iron-based superconductor a connate topology superconductor. This name is actually is created by myself. Okay, so now lots of people use it. So what means connate topology superconductors? So this is actually illustrated in these slides. So basically, if you think of a multi-orbital superconductor and with a non-trivial topological band structure, okay. So because it's a multi-orbital superconductor, and some band may responsible to superconductivity, but some bands they may be topological non-trivial. So this topological non-trivial band can create a surface state. And since the material in the bulk is superconductivity, this surface state has internal proximity effect, from his own bulk superconductors. And the surface state will become topological superconductors. So this is different from this. You using two materials to combine them, like a topology insulator plus like a superconductivity together. So this is a single material, it already has this topological non-trivial surface state, and it's already a superconductor and called topology superconductor. These are called connate topology superconductors. This is the picture illustrates. The bulk is a superconductivity, and you have surface state, and the surface state becomes a topological topology superconductivity. So in the iron-based superconductors, actually, it's very easy to look at these complicated band structures. If you look at the iron-based superconductor, we are focusing on the let's say the gamma points. Okay, the gamma point. You can see that there's like 5d orbitals. So you have these five bands. So where we look at these topological properties, potential non-trivial topological properties, is actually pretty simple. In gamma point, you can look at these the band parity characters. So here actually you can see as here we show there's like these three band, one on the above Fermi surface, okay, one is the solid one, and there are two another by dx dy. These upper ones are by dxy actually, and if you look at the parity, actually the top ones is parity odd, the lower ones are parity even. So immediately you know that if we have a parity odd and a parity even band, if they close to each other, then you will create a non-trivial topology, non-trivial topology, and with spin orbital coupling. Okay, so the key question is whether you can lower the top band, to meet these bottom bands. Okay, if you can meet, then they cross each other. Then you put a spin orbital coupling, they will create non-trivial topology. So this is actually can be achieved. For example, if you take an iron selenium and you use tellurium to replace the selenium, okay? And if you replace selenium, actually, very important is this top band. We call it A1U, which it will get lower, and to meet the even parity bands, and they cross each other. And roughly, the transition happens at x less than 0.7. Okay, so that will become the topological non-trivial. Okay, so that's in early days. The first paper was by my student Jiangping Hu, and also another group in Zhongfang and Dai Xidai group in IOP. And our paper was actually first posted online in 2014, and it got published, but for quite a while. But their paper actually posted later, got published first. So anyway, but the idea is the same. Actually, you can using this Terranian to make this band lower this band to close, making them close and create this surface state. Okay, and this is calculations. And then if you have the surface state, and if you using this Fleurkins argument that if you create a vortex, the vortex will trap the Majorana zero modes on the surface state. So this is actually a big progress now. In China, at least, we have several papers. The first one is by myself and Ning Hao when I was at Purdue, and we are doing this topology physics single layer RN selenium. So then we moved to bulk, and there's a lot of theoretical proposals. And the experiment actually, the first experiment to detect Majorana like zero modes is by Su Pan, and he was in Houston University and also in IOP. And Hong Dian, he was from used to be in Boston College, but now also in China in Jiangping University now. And Professor Gao, and there's lots of papers on these directions, also by Dong Lai and Qi Kun in China. There are quite a few experimental groups, at least observe these zero Majorana-like modes. So this moment, at least, I think RN-based superconductor is a new platform to study Majorana zero modes. There's also recently lots of experimental progress on these directions. But I try to move is to talk about second. Majorly, I will go talk about the second part, which is the topological and apparent symmetries, and this is more interesting to the theorists. I think we try to figure out how what's the apparent symmetries in these RN-based superconductors. So this. So Professor talking about is the nontrivial topology is came from the band structure. Okay, so the topological superconductivity is came from surface state. Okay, came from the surface. So there's no link to the pairing symmetries related to RN-based superconductors. So it doesn't matter what kind of pairing symmetry. It's just the nontrivial topology came from the band structures. So question here I try to ask is whether RN-based superconductor itself can be bulk topological superconductor. So there is bulk. So can they already be become a topological superconductor? So that's the next part I try to also address. This is the answer, of course, yes. If it's no, then I will not give these seminars here. So let's talk about the pairing symmetry issues. So the pairing symmetry is one most important characters for the superconducting state. As typically, like we have some conventional superconductors, typically are S-wave superconductors. So another different example is like these D-wave superconductor and these cuprates. This is another high temperature superconductors. And we now know it's a D-wave. And a D-wave means the order parameter. You rotate 90 degrees, you get a minus sign. Okay. And in the simple case, you can assume that there's a D wave form in momentum space. Okay, so the water parameter in momentum space is proportional to cosine kx minus cosine ky. And in the real space, you can view that there's a pair when the horizontal direction and the vertical direction are different. Because when the horizontal direction is minus, let's say vertical direction will be plus. Okay, so there's a real space sign change for the D wave superconductors. Okay, so if you have this real space sign change, this D wave, you can make a corner junction like this. You connect the X direction and the Y direction by loop mixed grid. Okay, and if you have a typical S wave, means you do not have the sign change, okay, as from plus to minus, like D wave here is from plus to minus, but here will be the same. So in that case, you will get if you measure if you apply a magnetic field and measure the current, superconducting current versus this magnetic field flux, and you will see a shift. Okay, so for the S wave, you will there's a zero flux, you'll get a maximum, but for the D wave, you will shift to the minimum. So you can easily see this real space sign change by these phase interferometers. Okay, and that is being proved in the cupolas in the 1990s. Okay, lots of experiment, and this is one. This is called phase sensitive experiment to measure. They prove that it's a D wave nature for the cupolate superconductors. So as I argued beginning, like this in the introduction, the iron-based superconductor actually does not have the nodes like in the D wave form. Okay, so it's a full gap superconductor, and that means no symmetry protection. So it's actually the S wave like. So what kind of S wave in the iron-based superconductor it is? Actually, it's very interesting. And so this is let's go back to look at the iron-based Fermi surfaces. So iron-based superconductor has this kind of Fermi surface shown here. So you have a hole pocket at a gamma point, like this, and the electron pocket at the brain zone corner, like here. So this you have hole pocket and electron pocket. Showing like in this typical case for the iron nictide. This is a typical Fermi surfaces. In fact, there's two classes of iron-based superconductors. One is the iron arsenic-based, as I mentioned. This is really like this. You have a hole pocket and electron pocket. Okay. And there's also a second class, which is typically these iron seleniums. And the first one is potassium iron selenium. Then later they have discovered many. And I call the second class iron-based superconductors. They are slightly different on Fermi surface. So Fermi surface is the second type of iron-based superconductor does not have hole pocket. They only have electron pocket, like this on the Fermi surface. Okay. So if you look at the pairing symmetry issue in the iron-based superconductor, in fact, one argument, one principle given is by myself and Hongdian and also Bernavik at very early days. So we argue that if you compare with cuprates, if you thinking about like a TJ model, the pairing. The pairing came from the antiferromagnetic exchange couplings. Okay, if is that the case, say in cuprates, the antiferromagnetic exchange coupling is from the nearest neighbor copper of atoms. Okay, so in that case, if you thinking about the pairing is pinned to the nearest neighbor to electron on copper paired. Okay, they have they can have S wave. They also can have D wave, like in real space like this, S wave like that. The S wave, the form factor will be cosine X plus cosine KY. And in the D wave, the order parameter will cosine Ks minus cosine KY. And if you look at the cuprates Fermi surface, these dashed lines, okay, you can plot these cosine Ks plus cosine Ky weight on this brane zone, okay. So you can immediately see that the Fermi surface is located on this S wave form factor. This the white place means the form factor is almost zero. So you can immediately see that if it's an S wave superconductor, you will do not open a big superconducting gap. Means you in superconductivity you will not save any energy. But if you look at the D wave form factor, you will get a very, very big gap on these antinode regions, like here. The form factor is very big on these antinode regions. So if you compare the D wave and the S wave, you can immediately see that the D wave will win in energy. So that's for the cuprates. Actually, a simple way to argue why the D wave is favored in the cuprates. But if you look at the iron-based superconductor, in fact, the antiferromagnetic change coupling is actually came from the second nearest neighbor irons. Okay, so like this. Okay, so then S wave will be has a form factor cosine k times cosine ky. D wave will be sine k sine ky. And then you can also look at the Fermi surface look at the overlap with these form factors. And you can see that for this form factor, the Fermi surface all located in the value of a large place. Okay, but for the D wave, if you have these form factors, they're all zero. They are located in these white regions, which the form factor is zero. So you can immediately see that in the iron-based superconductor, if from this antiferromagnetic change coupling it's a origin of superconductivity, it will favor this S wave. Okay, so that's a very simple case to understand the pairing symmetry issues in these cuprates and iron-based conductors. So if this is the case, this cosine times cosine k, cosine ks times cosine ky is the pairing. We could extend S wave pairing. If you have this whole pocket, electron pocket, this electron pocket, whole pocket will have opposite signs. Okay, so cosine k, cosine ky one, here will be plus, here will be minus. Okay, so if you have this first class iron-based conductor, they will call S plus minus. Here the plus, here will be minus. But if without the whole pocket, it will just standard S wave superconductors. Just there's no sign change in the momentum space. Okay, so that's actually a very simple one using this very strong antiferromagnetic change coupling to argue that the pairing symmetries. There's also another argument which came from the very early days by Igor Mazin and other many people from weak coupling argument. So if you have a Fermi surface like this, you have a whole pocket, electron pocket, and if it is a repulsive interaction is driving the superconductivity, you can argue that the repulsive interaction between the whole pocket, the electron pocket, is a player very important roles, and this is probably the driving the superconductivity. So in that case, you can also immediately argue that if they are repulsive, the repulsive interaction will favor this whole pocket electron pocket has different signs. Okay, so one got a plus, one got a minus. Okay, so that will immediately result in X plus minus, state. Same as the former this argument. But this weak coupling, the weak interaction prediction, this has a problem for the second-class RMS superconductors. Since the second-class RMS superconductors don't have this whole pocket, okay? So then they also high TC. So if you use the same argument, you have to think about how these electron pocket, they are, what kind of interaction can make. So if you using like simple theoretical models, you can fold out this pocket is look in the one island unit cell look like this. Okay, so one way you argue is that this two-hole pocket, if you using one island unit cell, these two-hole pocket. These two electron pocket can be interacting each other, right? So that will drive into these two hole electron pocket and these two electron pocket has different signs. Okay, so this will be D wave. Okay, so if you using same argument as before for the second class iron-based conductors, you will argue this will be the D wave. But certainly, the D wave is not supported by experiment because D wave still will create some nodes in the KZ directions actually. But it is so that time I think the weak coupling is not right. But later actually the Igor Mazin also make another argument. Let me show his another argument. Actually, he can argue that it is actually becoming another S plus minus state. This another argument is look like this. So you have this electron pocket at the corner, and they can hybridize. Okay, so if you have spin-orbit coupling and the two can hybridize, after hybridization, they can become two, one inner, one out, like this. Okay. So you can argue that the inner and the out, they are the positive interactions, and they will drive superconductivity. So in this case, they will become another S plus minus state, which is they have different superconductivity signs. So this I will call S star plus minus. Okay, so you have also have a sign change in the momentum space, but overall there's no real space sign change, right? So they are looks like S wave. Okay, so generally, if you look at the predictions, right, to S wave superconductor in RMS, they typically have these three scenarios. So one is like, without whole pocket, is just conventional S wave, no sign change, and with whole pocket you have S plus minus, whole pocket electron pocket will have sign change. Then there are also another S star plus minus wave, which you have two electron pocket that will have a sign change. So these three states. So the question is how we going to distinguish these three states, and whether there's a smoking gun experiment. We know that for the S wave, we cannot do the the real space phase interferometer. So what we can do? So here I try to tell you that we can do is using topological to differentiate these things. Okay. So the first one I try to distinguish is this S plus minus, okay, with whole pocket, and how we going to have a signature, topological things. So this is the summary of this paper we first proposed. So if the iron-based conductor is S plus minus state, like with this whole pocket electron pocket, and if you take this material, this is called the 112 iron-based conductor, and this if superconductor in this state, and then we claim this 112 iron-based superconductor will boundary obstruct higher order topology superconductors, and the simple prediction is that if you have this material, a piece of this material, and a corner in 1, 0, 0, 0, 1, 0 direction, this corner will attract robust corner Majorana zero modes. Okay. That's a prediction. So you can experiment to expose it to locate. But so far, this material actually hasn't been got a very good samples. So this experiment is still, people are still trying it. Okay. The second conclusion is that, so if the system like this without whole pocket, this system in this S plus minus star wave pairing state, if the ion is in this state, and we'll claim that this is superconducting state. Doesn't matter, you know, which RMB superconductor family you are taking, and this they will be intrinsic second order topological superconductors, and the experiment prediction will be in the 110 and the 110 corner will have the robust corner Majorana zero modes. Okay, so these two very specific predictions on this. So let me just quickly go through the theoretical things. So let me first discuss these 112 materials. So 112 material has this iron arsenic layer, and for given superconductivity, but they also insert this additional arsenic layer between these here. And this arsenic layer is actually inserted one as topological nontrivial, and you can take a look. This inserted one does not have rotation like C4V symmetry, and actually the crystal become monoclinic, which means if you think about it like these two arsenic, the middle ones shift a little bit, okay, create these things. And this material has like 40 Kelvin superconductivities. So this arsenic layer, additional arsenic layer, and provide also some band on the systems. And you can see here, you can notice that there's Dirac cone near the Fermi surface. Okay. The Dirac cone is located at this zone boundary at here, X point. And if you illustrate this is the Dirac cones here. And these Dirac cones came from these additional arsenic layers. And if you put a spin orbital coupling, you know, in the arsenic actually has a very large spin orbital coupling, and the immediate open a gap. The Dirac cone open a gap. This the gap is more than 100 MeV, and this is typical topological is actually a very good topological insulator. So this Dirac cones has been measured like in apex experiment. So by this mainly from Switzerland ETH, I think. So if you have this arsenic layer, they have this topological, it's a topology insulator, and then we can put this, so we'll have edge state, and in this edge state, this is, we calculate this there will be some edge state at the arsenic layer, and this edge state, and in the approximate effect by S plus minus wave pairing actually will be high order topological superconductors. Actually, this is pretty simple. So if you look at the edge state, if we at the X, you know, 100 direction is actually this edge state, this Fermi surface is located at the X point. Okay. And if you go to the edge state in the 010 direction, and this Fermi surface is actually located on the gamma point. Okay, so if you have this S plus minus superconducting state, since the momentum is is conserved, the one direction has still have this translucent symmetry, and at the x, and it will take this corner. The proximate effect from superconductivity will be from the electron point, and here at the gamma, and the proximate effect, superconductivity will from the gamma point, the center. Okay, so since the center and the corner has different signs, and you will actually create one edge as superconducting order, and another edge, they will have different signs. Okay, that's the key and observation for this edge state. So if you have these two superconducting order parameter are different, and at the corner they will form these Marana zero modes, like this. If you calculate the system, okay, so that's I will not go to details calculations, and this actually is very, very robust. If you put the non-magnetic disorder in this system, this corner state, they're very, very robust. And this is one calculation. You can see that there's a four state. Actually, it's 8 state. Okay, if you can consider spin and near the zero, which located under these corners. Okay, and the idea, if you take this STM measurement, you will should see a zero Marana peak in these corners. But experiment hasn't been studied this. Okay, so I still try to convince these experiment guys to make these better samples to do this. Okay, so let's move to the second part, which is this S plus minus star state and this prediction. Okay, so actually this is very interesting, and typically there's early days has lots of theoretical work discuss like what kind of superconductor will be topological and trivial. In fact, one conclusion at the early days theory make is that if you have a S wave, it's a A1G representation. Typically, in the group symmetry, we call it A1G representation. So A1G S wave pairing, and is from conventional theory thinking is actually is always topological trivial. Okay. So A1G S wave, you will not get topological non-trivial state. But this is actually not applied to the iron-based superconductor. Iron-based has a very interesting structure. This arsenic, half arsenic on selenium on top, half selenium on bottom. And this is so the lattice symmetry as a nonsymmorphic. This is very interesting features. So this nonsymmorphic lattice structure created something very early days. Actually, I used this nonsymmorphic group to discuss these symmetry issues in iron-based. This is very, very interesting. And one notice is actually this inversion symmetry in the iron-based superconductor is go to the between two ions. Okay, is between at the middle of the two iron bonds. Okay, not at the iron itself. So you have two group, one called D2D plus Z2. Z2 is exactly the parity. Okay, so you have this two group, direct product to each other. And if you consider these two groups, their elements, actually their commutation relations between these two groups at the zone center and the boundary will be different. That's the notice we so in fact very simple. So if you go to boundary, like if you think about ky equal to pi, and these two, so this one Miller symmetry and this inversion symmetry actually has they are anti-commuted, and if you at the zone center they are commuted. Okay, so in fact you can immediately notice that in that case, if you go to the gamma to the x gamma the direction, and it will be trivial. But if you go to y and my direction is a zone boundary, and you can actually become a topological non-trivial. Okay, so that's the formula to calculate these topological numbers. Okay, but I will not go details. If interested theoretically, actually, to these kind of things, after our paper, actually, this is my former students, some fun and Seychelles, they actually make a very, very nice analysis for this S-wave like topological superconductors using the Fermi surface diagonals to distinguish topological superconductivity. And their formula, they actually provide a very good formula here. But our case as a more simple here. So actually we can for our model we can create these write down these type of banded models like this, and you can calculate all these properties. So one specific thing is that if you the 1,0 edge, if you look at the 1,0 edge, and if you are in this S plus minus star state, actually you will get gapless modes. Okay, and when like Dirac cones on this edge state. But if it is 1,1 and 1,1 bar, direction this corner will have attracted Marana modes. Okay, from this theoretical calculations. So this result is only sensitive to this state, this order superconductor order parameter and the zone boundaries. So if you look at the specific predictions, the fact that you can just take this two-dimensional Allen Selenium lattice, and this is a 1,1 edge, and this is a 1,0 edge, and this is the corner. And our specific prediction will be at a 1,1 edge, it will be, the S plus minus star wave are the same. Okay, you will just look at the like S wave spectrum on that edge. But if you go to 0,1 edge, S plus will have just the conventional S wave. But if you have S plus minus, and you have the 0 modes, so the actual fail, the weight will not go to 0, so they will have some contributions. And if you go to corner here, if you measure STN, you will get Marana 0 modes like this. So for this on Selenium, you will get, you can using STN to take a look. And if it's in this state, it will show these features. Okay. So this is a summary of the theoretical predictions. So for D-wave, we have the phase-sensitive experiment to measure it. But for the iron-based conductor, if S plus minus, these two different S plus minus state, and the way you can do is that you can measure these corner 0 Marana modes if they exist, and you can prove this as plus minus. And in this case will be 1,1, 1,1 bar. Okay, this will be 1,0, 0, 1 corner. Okay, so that's very specific predictions. So for this S star plus minus, actually they have one experiment, and now we actually has done by Qi-Kun Xue's group, try to see whether this S star plus minus exists or not. The conclusion actually from we have their careful experiment result is this Arlen Selenium STO sample, at least is a simple S wave, not this state. Okay, so it's not this, actually it's topological trivial for this Arlen Selenium STO. Okay. So here's some experiment data. We try to look very carefully look at every edge and every corner, and the spectrum remains the same. Okay, so there's no gapless state at the 1, 1 edge. And if you look at the 0, 1, there's also no gapless state in 0, 1 edge. And if you look at the corner and they carefully mark, look at the corner spectrums, and there's no zero Majorana modes discovered. There's all these trivial, actually. So that tells you that the Arlen Selenium STO, at least this material is in this S wave state without sign change. Okay, so in that case, I will think probably this called extend S wave. This with a whole pocket is S plus minus. Without a whole pocket is simply S wave. It's favored in the iron-based conductors. So okay, so I think I already spent 50 minutes. So I try to tell you today is like there's a very rich topological physics in iron-based conductors, and the topological can be a quantity to be a smoking gun quantity to testify the pairing symmetries in iron-based conductors, and specifically in 112 material. If we can use to test this standard S plus minus wave, which has a whole pocket, electron pocket. They have between them they have a superconducting sign change, and this nonsymmorphic symmetry in iron-based conductor is very important, and it creates some topological state. If for this S star plus minus. Okay. And so far at this moment, this Arlen Selenium STO looks like simple S wave. It's not in this S star plus minus state. Okay. So finally, let me thank my collaborators. So this many theoretical calculations are really done by my student Jiangping Hu, Qin Shenzhan, and early days Ning Hao, my postdocs, and Chen Fan and Fu Chun in the KRTS, Capital Institute of Theoretical Science. And I have lots of collaborations with the experiment group, and Hong Jungao's group, Qikun Xue's group, Dong Lai Feng's Hong Jin's group, and Su Wenpan's group. Thank you for your attention.
Yeah, thank you, Jiangping. Yeah, very nice talk. So I think I understood your story. So let me sort of use as a host to ask you the first question. So in terms of the S, if you think the iron selenide is a simple S wave, so how do you understand the pairing media? I mean that would be against saying magnetism or anything to do with superconductivity, right?
No. It's still the same. If you're using my argument,
I thought you argued that you have to have a S star plus minus, right, to be anti-second year's neighbor, right? That's your argument, right?
No. Okay. So let me go back. So this is a difference. So yeah. So from my argument, if you from the second nearest neighbor antiferromagnetic change, right? J2. Okay. So then you form a pocket. You are even without a whole pocket, you just get rid of these ones, right?
Right.
So you have electron pocket here. The electron pocket still has a very large weight.
Okay.
For cosine K as cosine KY. So there's a doesn't matter whether you have a whole pocket or not. You just have electron pocket. You can still save very large energy from these antiferromagnetic exchange components. That's yeah. So from the weak coupling is a very if
almost
you have
impossible, right?
If a positive interaction, then it's impossible. So just like if you have to have somewhere sign change if you're using the positive interaction. This weak coupling argument. But for the very strong coupling, I don't think it's necessary.
But maybe I mean you said there's no direct evidence for sign change. I saw the neutron spin resonance was believed to be the sign change, at least indirect, right? Not direct, evidence.
Yeah, indirect.
Sure.
Yes, there's somewhere around it, So, in fact, this orange selenium, actually, the resonance also very complicated, right?
No, it only occurs in one direction. Only occurs in one of the the orthorhombic axis direction.
Yeah.
But that does that always mean that when you have a resonance, it has to have a sign change? That's in the weak coupling theory, right?
Not necessarily. So the science resonance, if it's based on this magnetic exciton, right? It's some kind of picture. But if you you can work other ways around it.
I see.
I think it's not definitely, if it's not the direct evidence, right? It's you can say that it's easy to explain if you have a sign change, right?
I see. Okay. So I mean that's why okay. Yeah. I mean the heavily doped, the stuff when there's no whole pocket, then you don't really see much of a resonance, I think. Yeah.
Yeah, you also don't weak, much weak.
Okay. And any other question for Jiangping or from the audience? With a lot of audience, but I guess today. Okay. Rob? Yeah, okay. You have a question?
I'm from Peter Armitage's lab at Hopkins. I was just wondering if you could comment on they seem to see, right, these like in iron selenium at least, like fluctuations above TC, this like linear in T resistivity and stuff, like alluding to like sort of this strange metal behavior in the Coop rates. Like, I don't know, have you all thought about that at all in this like deduction of the pairing symmetry?
I didn't, I can't hear clearly.
Yeah, so maybe you can repeat your question. You
can repeat your question.
Because I couldn't understand your question either. Sorry.
Okay. Can you hear me? Like,
sure.
Okay. Yeah. So my question just has to do with in iron selenium at least, they've seen this linear in T resistivity right above TC. Like fluctuations above TC and like maybe like it's allusions to this like strange metal behavior in the frequency. And I was just wondering if you have considered that in this like classification of the pairing symmetry in iron selenium. Were you able to hear that? Is that clear?
You mean? Can you repeat your question?
No, I can repeat. I understand his question. Basically, saying that the iron selenide, the resistivity is a linear behavior above TC. So and that typically people argue it's due to strange metal, right? I mean, do you have had any thought on that? He was curious.
Yes, exactly. Thank you.
Yeah. So actually, we had recently we had a paper which analyzing these linear things, especially these coefficients. Actually, looks like these coefficients of the linearity has something to do with TC. It's a correlation with the TC. It's actually, in that sense, actually, the cuprates and the iron-based superconductor all are same. Actually, we have these universal scaling laws and show these linearity coefficients that TC is correlated. Certainly, that will speak, I think it's a favor like this spin fluctuation kind of scenario to explain it. That's I can say. I will say, the mechanism for the iron-based cuprates should be the same. Okay, and there are lots. There's a lot of similarity between them, but the pairing symmetry, it could be different. That's because pairing symmetry is more collaboration between the Fermi surface and the antiferromagnetic fluctuations. It's not just simply, one thing determined. It also determined by Fermi surfaces. So that makes sense why RMS is going to favor S wave, cuprates favor D wave. Okay. I don't know. Actually, I answer your question. Yeah.
What's your thought on the nicolates? I mean, do you also believe it's a spin fluctuation driven jumping?
Yeah. I think Nicola will be no different from cuprates. That's my. Yeah, actually, people now, there's a nicolate as another issue came in is like this is double layer, right? Double layer structure. So this double layer, in fact, now if some people are now starting arguing this double layer coupling between these DZ square orbitals are most important, right? So in fact, that if that's the case, we had a paper now calculating the electron phonon coupling with DZ square will be very, very strong, and you should see the phonon softening on that case. But I still believe it's magnetic driven. So, but at least that will help rule out. The nicolate mechanism will be different from the cuprates. So that's what I can say.
What? Okay, yeah. Tama? Yeah. Tamagna?
Hi. So you talked about corner modes, and if I understood correctly, these are calculations done in 2 dimensions. If you have multiple layers of iron arsenide, do the corner nodes on neighboring layers talk to each other, gap out? How do you think of them in 3 dimensions?
Yeah, so if the coupling is strong, okay, then of course there will certainly affect these problems. But so far, we look at the layer coupling is in iron-based superconductor, especially iron selenium is very weak. So it's there's no need to consider the islands in this iron selenium case. But certainly, if you go to if you have this 1-2, like a barium iron arsenic, that kind of thing, the layer coupling will become important. So in that case, we did some calculations, for example, for the band topology. So for the first part, so for the band topology, we find that if you consider layer, actually can be coupling can be a controlling parameter. You can drive in the topological to non-topological transitions. Okay, but for the The later part we haven't done any calculations yet. Yeah.
Is the size of is the Majorana localization length that you estimate smaller than the c-axis lattice spacing of these materials?
I didn't estimate it yet. Let me see. Maybe not. Our view, maybe not. Corner. Let me show the. So let me. So my student.
I thought the thickness is not in your calculation, right? The thickness of the layer is not in your calculation.
Yeah, not in my calculation. So far for these kind of things, we are just doing these corner, not in C-axis, not consider C-axis couplings. So yeah, we here I think. I forgot, how much lattice we put in. This is the picture. We have this is simulation for the real, models. Okay, but I forgot the lattice size here. I can go back and check how big is the zero modes. Yeah.
Okay. Any other question for Jiangping? Okay. Yeah. If not, yeah. Thank you so much, Jiangping. Yeah. Good to see you.
Thank you.
Yeah.